Okay, let's continue. We've seen in the previous lecture that the set of all wave functions is a space, because the sum of two wave functions is a wave function, and they can be multiplied by a complex scalar. And we have also seen that the space of linear operators on that space is also a space. What we'll be busy with today is looking at dimensions of those spaces, and also looking at something which in magnetic resonance is called the superoperator space. It is a superstructure on top of the operator space, which will be useful in our practical calculations, particularly when we get to relaxation theory and other such things. So schematically what we had was the set of wave functions, psi, on which we defined addition and multiplication by a scalar, and then we had a set of operators acting on this space of functions and transforming it in some way. And we further noted that there are things called commutation superoperators, and we'll come across other types of superoperators at some point that act on operators and transform that space. So we have managed to make this into a Hilbert space by defining a scalar product in it, a metric, a norm, that was either an integral, psi was our phi dx, or it was a discrete sum if it was a discrete representation, which was denoted psi phi in general, and we had to integrate over all continuous variables and sum over all discrete variables, and that was our scalar product. So what we'll now do is look more closely at this and this, and what we'll do in particular is define a metric in these spaces as well to make them into Hilbert spaces. And so, analogously to this, we will define operations here which will give us the notion of a distance on those spaces, and which will make them into Hilbert spaces and allow us to work more productively as it were with them. Now, a bit of terminology. This space of operators over psi, because they're linear operators and they transform psi, is known as a space of endomorphisms. And V, where this is a space V. Now, then the space of linear operators transforming this space would similarly be an endomorphism of this, and so this is and V. In a special case where an endomorphism is reversible, so there is another endomorphism here which exactly inverts the action of a given endomorphism on that space it's acting on, it's called an automorphism. So clearly this is a smaller set because there are endomorphisms which are not automorphisms because they are not actually reversible. Now, one particular thing that we'd like to know is a dimension of this and this, given a dimension of this, and B, a way to build representations of these spaces and of the superoperator space, given a particular representation of the space of wave functions. In particular, we're interested in discrete representations because they are the ones that digital computers are most easily applicable to. So I'll give you a theorem which I will not prove. It's essentially a textbook statement from linear algebra about the dimensions of this. So if we have a space, it's called MNF, of all n by n matrices, and that would be the space of endomorphisms of an n-dimensional space of vectors, then the dimension of this space is n squared. It is relatively easy to prove because if you look at the matrix, which is n by n, then it simply speaking has n squared independent complex numbers in it, and therefore this is an n squared dimensional space over a field C in the case of quantum mechanics. And more generally, the space of endomorphisms of an n-dimensional space is n squared dimensional. Now this has a corollary in that this space here and p. So if this has dimension n, this will have dimension n squared. Now, because this action is just a copy of this action, there is nothing particularly special about a space of endomorphism acting on a space, then the dimension of this will have to be the square of this, and so the dimension of the superoperator space is n to the fourth. Clearly a huge number if the dimension of this space is significant. And because of the isomorphism that we've noted in the previous lecture, that an n-dimensional space over a complex field is isomorphous to Cn, then this would be isomorphous to Cn, that would be isomorphous to Cn squared, and this would be isomorphous to Cn to the fourth. And so because they're now isomorphous to complex vector spaces, we can actually type them into a computer, and they will be matrices and vectors, and manipulate them there with relative ease. Now, so this is the space of wave functions, this is the space where the operators live, and this is the space where the superoperators live. And in quantum mechanics, colloquially, this construction, just these two wave functions and operators acting on them, is known as the Hilbert space picture. We sometimes use it in magnetic resonance for simple calculations. However, this construction, where we've got the superoperators and operators, so we have a density matrix which lives here, and we have superoperators acting on the density matrix, and maybe some operators to multiply it into. We'll get to algebras in the next lecture. This construction is known as Liouville space picture. And this is where perhaps the more sophisticated theories of magnetic resonance live. In particular, a relaxation superoperator belongs here. It's not even a commutation superoperator, it properly populates this dimension n to the fourth. Density matrices are here, and then the underlying wave functions, if ever our system isn't actually an ensemble, would live in this place. So, when you read textbooks, when you read papers, you will often come across this transition between Hilbert and Liouville space pictures. Now, of these superoperators, it is actually possible to express the action by a superoperator in a certain general way. Not all of them are commutation superoperators, but in the most general case, a superoperator P acting on an operator rho can always be expressed like this. It will be a sum over n k, p and k, where this is a complex number, m and rho, m k, where these matrices m k belong to the space m and c. So any superoperator here can be expressed as such a combination with complex coefficients of the operators living here. And you can see it's a double sum, so it will have the square of the number of the elements of this space. And if we have an n squared dimensional space here, the number of the terms in here will be n to the fourth in the most general case when all p is non-zero. And so the dimensionality argument holds in that this would be a considerably more flexible construction than just a multiplication by any operator in here. What this will allow us to do now is to build representations of this space. Clearly, this is a fairly cumbersome construction. So if we were to define a superoperator like this, we would have to stockpile an array of these coefficients. We'd have to stockpile an array of matrices that these coefficients are referring to, and then compute such a sum every time we would like to multiply an operator into a superoperator. And it's, for purely housekeeping reasons, not a very good idea. If you ever would like to exponentiate this, for example, exponentiate the other thing about it that it's not always linear with respect to these two things, and because it has to be a linear space, clearly a better representation is in practice required. So let's now take a look at the following procedure. I guess it can be called characterization and doesn't have a proper name. If we take an operator, which is a matrix, from here, it will be acted upon by some superoperator in a linear fashion. But it is a matrix, and this would have to be a matrix, cube of numbers, having 4 dimensions, not very convenient. So why don't we make this into some kind of vector? And if we succeed in making this into a vector, then the operators here would simply become matrices, because endomorphism of vector space is a member of a matrix space. The way this is most commonly done, at least in quantum mechanics, is to stretch this thing column-wise. So what we do is we take this column here and number 1, and we take this column here and it will be number 2, and so on, and we just put them vertically on top of one, 2, and so on, and that the final column here. Clearly we haven't lost anything. There are still numbers, the same numbers as we originally had. We'll clearly have to modify our algebraic operations to account for the new structure of this representation. But it is now a vector. And so any linear operator acting on this must then have a matrix representation. And again, the dimensionality argument is fine, because this will have n squared elements, and therefore will be n squared dimensional, and so the space of matrices acting on this will be the square of that dimension, and so n to the 4th. So we would now, therefore, like to build a representation of these operators on this stretched matrix space. So it's huge matrices acting on these things, and they are really, really, really huge. If it wasn't as far as matrix storage and practical applications and software like MATLAB, life would have been very difficult indeed working with these things, because the dense representation overflows computer memory in absolutely no time. Right, so to that end, there is a very nice theorem that if we have an operator, a superoperator, C double hat, acting on an operator rho, such that it accomplishes the following action. So it's A rho B. So a superoperator C is defined as such a superoperator as multiplies rho on the left with A and on the right with B. And then the matrix representation of C in a stretched basis will be the following. C double hat acting on rho, and I will use Dirac bracket for a stretched representation because it is then a vector, and this is a standard notation for the vector in quantum mechanics. So rho is the following. It's B transpose, not conjugate transpose, just transpose, cross direct product of the kind that we saw in the previous lecture. A rho. So a very simple thing, where rho vector is obtained from rho matrix by column-wise stretching of the elements. MATLAB has a beautiful operation for that. If you have a variable called matrix, which is a matrix, then you just do this, and it ends up stretched, because MATLAB stores things column-wise. So column first indexing. And so this transformation in MATLAB literally amounts to just doing this, and then we have to cross these things together. Well, this is something that is very perhaps central to spin dynamics, and so unlike the previous textbook algebra, I will actually give a proper proof here in terms of index notation, because it is clearly quite educational to how these index transformations are done. Most advanced software packages that work with usable space will have this as the first step in almost any calculation. So let us do that properly. Okay, starting here. So this is still a matrix, it's a super operator acting on a matrix, and so the result is a matrix. So we'll have a C double hat row hat, and we would like to know the element ij of the result matrix. We'll now have a rather arcane index transformation here, so I have to make sure I actually follow my own handout because it's rather easy to get lost in this. Right, so an element ij of that will equivalently be an element ij of this, of course, which is a simple sum over all the inner indices. So I use k here, row k n, b n j. You see, it's a fairly standard situation. If we would like the indices ij of this, and that's a matrix product. I is on one side, j is on the other, and all the middle indexes are summed over. Because this is a sum, we can collect the individual numbers in each term, so there is sum over k n here, a sum over k n, in brackets a I k, b n j, then row k n. Okay, so this is still matrix notation. So what we now need to do is first re-index our row in a linear way. So this was element 1, 1, this was element 1, 2, 1, 3, 2, 1, and so on. But what will now happen is it becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, linear column-wise indexing. For that, well, it's a fairly simple thing to do. If we know the matrix dimension, then it will be the matrix dimension times the column number plus the row number for each here. And so we've got the following fairly simple transformation for linear indexing. So what we'll have is row will be re-indexed by an index s. So s would be equal to n, the matrix dimension, then j minus 1 plus I. So that's a re-indexing of the ij, and then r index would be n minus 1 plus k. So that is the re-indexing of the n k pair of indexes. Equivalently, what we can now do is do the reverse transformation. So given the indexes s and r, we can recover I and j from it. It's a bit of a funny operation here. You know, in floating point numbers, of course, this would be undefined because there are too few equations. But in integer numbers, we can actually solve this. For example, I is the residual of dividing s by n, and j is the divisor without the residual of dividing s by n. And so what we've got is, so equivalently, when we reverse these things, I is what's known as r modulo n, and j is r div n plus 1. So if we divide r, that shouldn't be r, that should be s. So I equals s modulo n. So if we divide s by n, then I is the residual of that division. And j would be again s div n. So when we divide s by n, that's the integer part of the resulting division operation without the residual plus 1. And similarly for the other pair of indices, so we'll have that k is r modulo n, and similarly n small is r div plus 1. So we've got the forward index transformation here, and we've got the backward index transformation between the row column indexing and the stretched column-wise indexing. And what we'll now do is plug this into here and try getting the linear indexing notation. Okay, so in the linear indexing, the result of acting by C superoperator on a row will be a vector. So it will be indexed by a single element R, and that must be the result of applying a matrix CRS, row S, and sum over S. Well, we've got on the one hand this C row ij gets into C row R, and so we've got a transformation here, so ij. On the other hand, we've got this here, and row must be reindexed in a linear way, so kn should be reindexed into S, and then CRS becomes this, which is reindexed for A and for B separately into the sequential indexing. Right, so then C n j minus 1 plus I, that's the first index in the linear indexing, n minus 1 plus k. So we have re-indexed element SR of the superoperator must be equal to the element here. So A, I, K, B, and J. And for convenience, because we'll get now to it, to the index mention, I will transpose B. So it will be A, I, K, and then B transpose element J, and J, Jn, it's just been transposed. So let's take a look at the resulting matrix C. It seems to have firstly blocks which are sized n by n, enumerated by an index j and an index a, n. So C will have a block structure. There will be big blocks. And the pair of indices enumerating those blocks is j and n. Inside each block, as soon as the number j and numbers are fixed, inside the block, the numbers are enumerated by I and k. So let's say the position of this block, the row position, will be determined by j. The column position of this block will be determined by k. And inside that block, by n, and inside that block will be enumerated elements by I and k. So I for row and k for column. Well, we've got ik being A, so these blocks, it turns out, will be copies of A, because A is indexed by ik, and so are the blocks. But each copy of A will be multiplied by this element, which is Jn. So this will be multiplied by Vjn. So see, the structure of the resulting matrix is multiple copies of A multiplied by individual elements of B transpose. And that is the structure of a Kronecker product. We know how we compute the Kronecker product. We take the first matrix in that Kronecker product and spread it out, and then we take copies of the second matrix and multiply it into each element of the first matrix to create a block, blocks of blocks, and put them together. So if we look at the structure very carefully, that is in fact the structure of the following Kronecker product: B transpose cos A, and that is exactly what this theorem was stating. So, okay, we have now built a representation of such a superoperator in usable space. One particular thing that we will now need it for, and that will be a corollary to this theorem, is a representation of a commutation superoperator in usable space, which is extremely useful in all practical applications. You see, the proofs are fairly involved, but really at the stage when we are simulating these things, particularly in MATLAB, which is amazingly good with matrices, it's just single line statements which do all these transformations. So let's take a look at the commutation superoperator. What we have is H superoperator rho is defined as H. Rho minus rho H. To bring it a bit closer to the statements that we've just proven here, which has A and B on either side of rho, what I will do is I will rewrite this like this. It will be H rho identity operator minus identity operator rho H. And you see we've got just two terms each of this exact type. So I will just rewrite that A rho B is represented by B transpose cross A in usable space. Well, let's take a look at this. What we now have is A is H and B is E. So what we'll have is E transpose cross H acting on rho minus A is the identity and H is B. H transpose cross the identity acting on rho, and that finally, because the transpose of a unit operator is equal to unit operator, is E cross H minus H transpose cross E acting on rho. And so the final corollary is the matrix representation of the Hamiltonian commutation superoperator is E cross H minus H transpose cross E. This is very, very important. And there is also a fairly popular mistake that people make. Of course, for Hermitian operators, H transpose is equal to H conjugate. So people commonly replace this transpose with a conjugate. And this is a dangerous thing because it will break as soon as H is no longer Hermitian. And so this particular formulation should be used in all cases to avoid those pitfalls. Okay, that's the representation of the commutation superoperator. Where it's useful in practice, of course, is time propagation, because what we have is rho t plus delta t, as we saw many, many times in the previous term, is E minus I H delta t for a static Hamiltonian, rho E plus I H delta t. So double-sided propagation, not very convenient, but it can be recast in a single-sided form using superoperators minus I H double hat delta t. So, and that is much more convenient for practical calculation because it's just one one-sided operation, which can be straightforwardly inverted and integrated and so on and so forth. This is really quite messy and cumbersome in practice. And then, well, this is then defined. We know how. A sum from n equals 0 to infinity minus I h delta t to the power n over n factorial rho. And then powers of the commutation superoperator are simply nested commutators. And so what this will work out to is sum from 0 to infinity minus I delta t to the power n over n factorial, h commutator, h commutator, h commutator, and so on, h commutator rho. The brackets have to be closed, so n-fold nested commutator, the so-called Hausdorff series in nested commutators for the exponential of the commutation superoperator. Another practical consequence of this corollary is this wonderful statement, which you can prove yourself. It's a very straightforward thing to do, that the exponential of this L cross E, so where these are just operators, plus E cross S, notice plus here, is equal to the exponential L cross the exponential S. Now, quite a few superoperators have this special structure, and so it's not in fact necessary to compute an exponential in an n to the fourth dimensional space. It is sufficient to compute the exponentials in an n squared dimensional space and then cross them together, which is computation much more straightforward from the purely numerical perspective. And so we can just adapt this to here, for example, to the calculation of the propagator, and we get the following equation. So the exponential of this propagator, this matrix here, so minus I E cross H minus H cross E, so H transpose here. We just match the notation, we can absorb the minus into the definition of the operator, so it becomes a plus, and what we get is an exponential of I H, should be T here, I H T, cross the exponential of minus I H transpose T. Now, clearly, it is much easier to compute the exponential of the Hamiltonian operator than to compute the exponential of its superoperator by root force, and then you can cross it afterwards. So it saves time, saves memory, and is generally slightly more convenient in a numerical context. Okay, so what we've done now is we have looked quite carefully at the space of superoperators and its representations, particularly in a way which stretches the underlying operators into a column. What we would now like to do is to make both spaces, the space of operators and the space of superoperators transforming it, into Hilbert spaces. And for that we need a scalar product. Now, you can probably see how we're going to do it. I mean, we've stretched it into a vector, and vectors do have scalar products on them, already known about. So we now proceed to define a scalar product between operators and superoperators as well by extension, but for superoperators repeats the same construction for matrices in degree dimension. That will be about it. I gave the definitions of a correct scalar product of an operation that is called scalar product. It has to satisfy, as you remember, quite a few relations in terms of linearity and positivity and triangle conditions and so on for it to be a valid scalar product. And so what we'll now do is define an operation that does the same but on a space of matrices. And then we have a notion of a distance, and then we can compute the expansions and integrals, various other nice things on the spaces of operators and superoperators. Okay, what I'll do is I'll remind you the 5 essential properties that a binary map from a space into the field must have in order to qualify for the scalar product. And I will do it now in magnetic resonance notation, and so we're slowly departing from pure algebra and drifting into the actual spin dynamics context. So let's do it. The 5 properties are, so property A, that for any operator living in the n-dimensional, in a matrix space transforming an n-dimensional space over the field of complex numbers, a scalar product of that operator with itself must be greater or equal to 0. B, for any 2 operators, L and S, living in M and C, it must be the case that the scalar product Ls is equal to the scalar product SL complex conjugate. I will skip the ahead, so it's too much hassle to write them. C, for any 3 operators L, S, I living inside M and C, and for any pair of scalars alpha and beta living inside the field of complex numbers, we must have the distributivity law, that is L scalar product alpha S plus beta I must be the same as alpha L S plus beta L I. So distribution. Then D, for any operator L living inside M and C, it must be the case that L be identically 0 leads to L be 0. So the scalar product with itself can only be 0 if the underlying operator is 0. And finally, E, the triangle relation for any L and S living inside M and C. It must be the case that the norm of L plus the norm of S is greater or equal to the norm of L plus S, where the norm of L is defined as the square root of the scalar product of L with itself. Okay, quite a list to satisfy, and there are an infinite number of possible binary maps from M into C that satisfy these conditions. However, the physical nature of quantum mechanics and the probabilistic calculus that is inherent in quantum mechanics thankfully constrain the choices, and the only scalar product that satisfies both these relations and plays nicely with quantum mechanics is the following. L scalar product S will from now on be defined as a trace, so sum of the diagonal elements, of L Hermitian conjugate S, where the Hermitian conjugate is a conjugate transpose operation. So you conjugate every element and then transpose the matrix. So this is the scalar product on the space of matrices, or equivalently operators. Right, well, we can prove a few properties about it. We can, well, let's for example prove this. Property A, property C, for example, is trivial. It's just a linearity. And because the trace is linear and the product is linear, so it's not a big deal. But, well, positivity we can, for example, prove. So, the trace of L Hermitian conjugate L is, from the definition of a trace, it's a sum over K and N. L Hermitian conjugate element K, and then L element K N. But Hermitian conjugate is a conjugate transpose, so we have a sum over K N, L star K N, L K N. That's just the square modulus, so it will be a sum over K N, L K N modulus squared, and clearly that is greater or equal to 0, and only 0 if all these numbers are 0, and so the matrix is identically 0. So we have proven this, we have proven this. This is trivial, you can do it yourself. This is trivial, you can do it yourself, because if you just swap them around, then one of them acquires a star, and the other loses it, so we got this. And the final thing that requires a bit more thought in proving is the triangle relation. And let me just wipe the board and put it there. Interestingly, even though the scalar product is defined as this trace, it is very rarely actually computed that way. You see, computing it as defined will require a matrix-matrix multiplication. And then we'll throw away most of the elements, we'll never use them. Because the trace is only requiring for its calculation the diagonal. So you see, we're computing n squared elements for an n by n matrix, but we're only using m of them. So clearly a big waste. And a better way of computing that scalar product, as we'll see in a moment, is the so-called Hadamard multiplication, which, unlike the trace definition, only requires order n squared elements, or order n squared multiplications, but this actually requires order n cubed. Right, so let's prove the triangle relation. What we'll have is modulus L plus S squared. We'll just square the norm, and the norm squared will then have to be norm L squared plus norm S squared plus the scalar product L S plus the scalar product S L. So just the usual square, taking into account the fact that this operation is not commutative, but it's commutative with a conjugate. So they're strictly speaking different numbers. Well, this is clearly less than or equal to modulus L squared plus modulus S squared plus 2 modulus L modulus S. Because a scalar product is always smaller than just the product of the lengths of the two vectors. Put it here to make it a little bit more readable, which is modulus L plus modulus S squared. And so when we take the squares off, we'll arrive at this statement here, given that all the moduli are always positive or identically zero. So this scalar product satisfies the properties required. And now back to the Hadamard multiplication. So it's defined like this. L, this multiplication sign, so spot-on multiplication. S is defined as an element-by-element multiplication of the two matrices, which are then summed, the result is summed together into just a number. So if we multiply the elements directly on top of one another, so n k, L, n k, S, n k. So you see we multiply them element by element and sum together all of the resulting elements. With that kind of definition, we can easily rewrite our trace like this. Trace of L Hermitian conjugate S. So from this definition here, from the definition of a trace is a sum over nk L star nk S nk. And you can see it's the same kind of structure, except we have L star in here. If we reindex it in a linear fashion, it will equivalently be a sum over n, L n star S n. So where we have a single index indexing the matrix column-wise. So this, for that reason, is just L star dot S. Well, star denotes just conjugation without any transposition operation. So you see a matrix multiplication here required O(n) cubed multiplications, but the Hadamard multiplication here only requires O(n) squared operations, the O(n) squared multiplications. Additions are rarely counted in computer science because they are very, very fast, much faster than multiplications. Okay, particularly particularly, well, one other thing to note, this is really good for sparse matrices, because spot-on multiplication of sparse matrices can simply ignore the elements, whereas the element of the other matrix in the corresponding position is 0. And also, whereas this requires fairly chaotic memory access patterns, one matrix has to be indexed across the rows. For this, particularly in sparse cases, the memory access pattern is always linear. So when you're computing your traces, please take advantage of the Hadamard multiplication because it's considerably faster. Okay, so, well, we have defined an inner product on the space of operators, and really the inner product on the space of superoperators is defined identically. So first thing you do is you find matrix representations for superoperators, and the second thing you do is you multiply them together and get the trace. And even with higher order constructions and hyperoperators, they're not very often encountered, but I've only seen them once in a pretty convoluted piece of theory. But given any given any matrix space, this is how you set up a scalar product inside it, and then it becomes a Hilbert space, and then basis sets can be specified and expanded with respect to, and so on. I've given you a summary in the handout of Hilbert space, Liouville space, and the superoperator space, along with both continuous and discrete scalar product defining it, and the corresponding dimensions. Right. Now that we have this scalar product, we also have the norm. Here it is, and the next topic is a fairly notorious confusion, which almost every researcher had to go through at one point or another in his life. If he did any NMR or EPR simulations, you see, in linear algebra, it's quite convenient to work with orthogonal and normalized basis sets. So convenient, in fact, that the first instinct of any person doing these calculations is once he picked up his basis, he would like to normalize that basis. Or once he has picked up a set of operators to work with, his first instinct is to normalize them. Well, that's a fairly easy thing to do. You divide the operator by the square root of its scalar product with itself. However, what you immediately find after doing that is the commutation relations get broken. That is, normalized Pauli matrices, for example, no longer commutes the correct way. That is the commutation of Lx with the y is no longer ILZ. Well, thinks the researcher, what's it help? I've normalized my matrices, so I've done the right thing from the algebraic point of view, but hey, physics got broken because the commutation relations no longer hold. So, well, he decides to uphold the commutation relations because after all he's doing physics, and discovers that the matrices are no longer normalized. So that became, well, I called it normalization commutation dilemma, and it simply states that in spin dynamics for spin operators, unit norms are incompatible with the commutation relations. Very easy to prove if you write out things like this, Sx, Sy commutator, you know that that's I, S, Z, and if you write them out, Sx is 0, half, 0, and Sy is 0 minus I over 2, I over 2, 0, and Sz is a half, 0. They all have the same norm, so, well, let's, for example, compute the norm of S. So trace of Sz Hermitian function. Z is a Hermitian matrix, so it's just a trace of Sz squared. That is therefore a quarter plus a quarter. That is a half. And because the norm is the square root of this, what we have is 1 over root 2. A very strange normalization for this. So we can think, okay, if we multiply Sz by that, it will start having a unit norm, but what will happen is the commutation will be broken. And if we normalize these and take sequential commutators, then the coefficients will accumulate and you eventually end up with 0. So Well, bottom line is normalization destroys commutation, and what makes matters worse is how many matrices for different spins have got different norm. So this was SZ half. If we take SZ for spin 1, that was 1, 0, minus 1, and calculate the norm of that, we'll immediately discover that the norm is in fact equal to not 1 over root 2, but root 2. Yeah? This squared plus this squared is 2, and then the square root is root 2. So norm of SZ for spin 1 is root 2, and easy to see that the norm of SZ for spin 3 halves is then root 5, and so on. So you see the norms drift with representation. But really for angular momentum operators, for example, we didn't actually have any specific angular momentum in mind, and it could have changed. Spin is intrinsic and unchanging, but angular momentum isn't. And you can imagine the sort of nightmare you're going to have if you try to normalize this matrix. So the bottom line for this is don't try ever normalizing your spin operators. There's a good reason for it, and we'll get to it when we get to Lie algebras, but in spin dynamics, these commutation relations are much more important than the norms. Norms are fairly easy to work around. You just have to divide by the norm every time you're doing some kind of expansion. But the commutation relations are fairly precious, and things break in pretty dramatic ways if your commutation relations are not high. So make sure your commutation relations are correct, and do not make any attempts to normalize your operators in any practical simulation. You will save yourself a considerable amount of trouble. Right, the final thing for today is a list of common basis sets. Now we could simply use this. So these have been written in a simple alpha beta basis set. So this is for alpha and that is for beta. Should be minus here. But that's very infrequently actually the best possible basis set. So there is a fair number, and I'll just give you a couple that happen to be, I guess, the more useful in practical calculations. The choice of the basis set is dictated purely by the physical nature of the system, and also by the numerical convenience of carrying out the corresponding simulation. Generally, we would like to avoid very fast dynamics. So if we have, for example, a Zeeman interaction, which is a gigahertz, it would be pretty difficult to calculate if we actually have gigahertz scale dynamics in the system. So people use rotating frame approximations and secular approximations to try and make the basis sets that they've chosen either invariant or slowly varying with respect to time. So ideally, the best basis set possible is the basis set that is completely stationary under all interactions in the system. And it's fairly easy to at least write the definition of, because our Liouville von Neumann's equation d rho by dt is minus I h rho. The operators that are stationary are the operators that compute with the Hamiltonian, because then the derivative is 0. And so the best possible basis set is the basis set that would commute with the Hamiltonian, or equivalently live in the null space of the Hamiltonian commutation superoperator. So HSK would be some eigenvalue HK and region SK. So if your basis element is stationary under this Hamiltonian, then there will be no dynamics between the elements of the basis set, with the exception of the complex space that will accumulate. Now, that would be the best basis set from both the physical and the numerical perspective. However, this is essentially an eigenvector problem. So HSK is HK SK. And typically the dimension of this H, it can go into millions. And so it's not in practice diagonalizable. And even though this is the best possible basis set, it is often impractical to actually obtain it. And so people make do with basis sets which are invariant under several parts of H, but needn't necessarily be invariant under the whole of H because of the computational difficulties associated with solving this. So A few of those. So one basis that is invariant under the frequently dominant Zeeman interaction is the direct products of S plus, S minus, and Sz. So not Sx, Sy, Sz, but S plus, S minus, Sz. The reason for this choice, and the reason why we tolerate non-Hermitian operators in the basis, which causes a few things that have to be carefully worked around in practical calculations, is that this basis is invariant under the Zeeman interaction. So if we take Lz L plus, that's L plus. If we take Lz L minus, that's L minus, and clearly Lz commutes with itself. So L plus would acquire a phase, L minus would acquire a phase, and Lz wouldn't even move at all. And because Lz is often the dominant interaction in magnetic resonance, those very gigahertz of Zeeman interaction, even pushing terahertz in EPR, this slows down the dynamics considerably from the numerical perspective, because this is invariant under Zeeman interaction, and the only thing this is not invariant under is the couplings. But the couplings in nuclear magnetic resonance are between hertz and kilohertz, which are clearly better than gigahertz. And the couplings in ESR are the order of megahertz, again considerably slower than terahertz. And so the dynamics in this basis set will be orders of magnitude slower than the dynamics in the XY basis set, because this X and Y will be interconverting between one another at that magnet carrier frequency. So you'll be able to make practical calculations a much longer time step, and therefore much fewer matrix multiplications, and therefore have a simulation which runs considerably faster. Now, this basis, it usually also involves the unit operator for the reasons which I will discuss in the following lectures. It's clearly just a single spin, and as we discussed in the previous term, if we have multiple spins in the system, then we'll have direct products of this. So if we've got 4 operators on the first spin, and maybe 4 operators on the second spin, there will be 16 operators, so all of their cross products for a 2-spin system. And on it goes, it will scale exponentially. Unfortunately, with the number of spins. Now, the other basis that people often use, and the basis in which these operators are in fact written, is the alpha beta basis set, or equivalently the total momentum, or the individual momentum representation, things like LL. So alpha beta is a special case of this for L equals L. What we can do is, as we did when we derived our Pauli matrices, we can take the top state, so let's say it will be LL, the height projection, and call it 1, 0, 0, and so on. 0, we can take one state lower, LL minus 1, and call it 0, 1, 0, and so on, 0. And finally, when we get to the bottom state, L minus L, we'll get is 0, 0, 0, 1. And as we did with the Pauli matrices, representations of operators can be built in this, which will look like that. For any operator S, it will have an expansion, M1, M2, summation, some coefficients, matrix elements, A, M1, M2, and then a pair of projectors, L, M1, and L, M2. So what this will do, it will project out state LM2 and forward the result to state LM1 with the corresponding coefficient. For that reason, this is, for the reasons why it has projectors in it, this is called a projector basis set. Not often useful because, as I already pointed out, it tends to have pretty fast dynamics in practical calculations. But if you don't have any fast dynamics in the system, then really any basis set is just as good as any other. Okay, that's it for today, and the next lecture will be dealing with groups, finite groups and the continuous groups. Imposed the orthonormality